Hello, AP Calculus students. This is Mr. McAllen, and this is day 2 of our review for the AP Calculus test. And we're going to use this question from AP. It's from 1984. It's quite a while ago, but it just goes to show you that the questions don't change all that often in terms of calculus content. What we're going to do, the objective here is we want to draw functions from first and second derivative data. Remember, you always want to read all of the information that's given in the question and if you find that there's information that you did not use, I would really question whether or not you will always need that information to help you with the problem. So I would always question if there's a piece of information that you didn't use. I would try to go back and use that information in the problem somehow. So what we see here is we have a question given to us where they're telling us about the first and second derivative. And in the beginning, don't forget to read the part above the table. They tell us that the function is continuous on a closed interval, and they give you that interval. And they say that they give you some data points for the function. They tell you that the first and second derivative have the following properties given in the table below. For part A, they want us to find the absolute max and absolute min points on the interval from -3 to 3 and to justify our answer. I'm going to come back and do that as the third part of the problem because I think part B and C are easier to do first. So for part B, it says what are the coordinates of all points of inflection for f on the interval from -3 to 3? Justify your answer. Well, to justify your answer for points of inflection, all you have to show is that the second derivative changes sign. So if you scan your information for the second derivative, you could see here that the second derivative is positive, fails to exist, and this would be a hypercritical point, so that's a point to check, and then it stays positive. So there's no point of inflection at x equals -1 because the second derivative did not change sign, but the second derivative did change sign at x equals -1. So you would say for part B, at x equals +1, there is a point of inflection at x equals 1 for f of x because f prime prime of x changes sign. For part C, they want us to draw the function. So I think drawing the function is easier to do first, and then that will help you explain where your absolute max and min is for part A. So let's just, it says on the axis provided, but there are no axes provided on this question sheet. So I'll just draw my own set of axes. And the first thing I want to do is use the point f at -3 equals 4. So it's just a sketch. F at 3 equals 1. So I have -3 comma 4. I have 3 comma 1. And I'm going to use the first derivative in the interval from -3 to -1 to show me that the function is actually increasing. So I'm going to use a different color ink. So it's increasing up until -1, and then the derivative fails to exist. The only way derivative can fail to exist is if you have a corner or a cusp or a discontinuity, but because they told us that the function is continuous, I don't have a discontinuity. So now the derivative goes negative, which means the function starts to drop on that interval. So here it is going to drop, and then at 1, it has a 0 slope. And so I'm just going to put a 0 slope indicator, and then it continues to drop on the remaining part of the interval. So I'm going to fill in the concavity. So the second derivative tells me that I have upward concavity. So instead of drawing this dotted line, I'm going to draw an upward curve, upward concave shaped curve, and then fails to exist. So that's, again, if the first derivative failed to exist because of a corner, the second derivative will fail to exist. And then coming out of that point, I have upward concavity again, because the second derivative is positive. Then I go to a 0 second derivative, which just means at that point I have no concavity. and then I switch to a negative concavity, and that would be that point of inflection we talked about. And from this picture, you can see that we can clearly identify our absolute max and our absolute min. So how do we explain that? So part A, we're going to go back and explain part A, and we're going to say that to basically justify an absolute max or an absolute min, you have to say something about the closed interval method. So I would say the function will have max and min values at either the endpoints of the closed interval or at the critical points within the closed interval, because the function is continuous on the closed interval. So what this means is, if a function is continuous on a closed interval, it has to have an absolute max and an absolute min. And the places that you look are at the endpoints or at the critical points. So we're going to make a table. Using a table of values, I can identify those points. So my table, I'm just going to draw it right next to here. I have x and f of x. I want to put on the table my endpoints. So my endpoints are at -3, I had a value of 4. At 3, I had a value of 1. And at -1, I had a value larger. I'm just going to do value greater than 4. And I'll justify that in the statement. And then at my other critical point, which was at 1, I had a value between between 1 and 4, or between 1 and f at -1. And that can be justified by using the first derivative and saying that I know my maximum value is at, the max value is at x equals -1, because the function originally had a value of 4 at the left endpoint and increased until x equals -1, because the first derivative was positive. The remaining function values went down, decreased on the interval from -1 to 4, to 3, because the derivative was negative. So because of this, you know that the maximum value was at x equals -1. The minimum value was only to be found at the endpoints because at the critical point x equals -1, that was a local max, which turned out to be the absolute max. And at x equals 1, that was neither a local max or a local min. Because the first derivative did not change sign. And as indicated by the drawing, the absolute max was at the right endpoint. Absolute max is equal to 1 at x equals 3. So hopefully this explanation, although it's wordy, it helps you understand the way that we explain using data and the tables, how to figure out our where our relative extrema can be. Remember, this is all based upon the closed interval method. So remember to always cite the closed interval method as helping you figure out absolute maxes and mins, and the conditions for that are a continuous function on a closed interval. I hope this video has helped, and I look forward to hearing your comments.